All right, let's go through this problem that you've been working on. Again, this was a practice problem that I suggested and I wrote a key for, and I hope you did look at it and think about it before this point, and maybe even try it before this point. Practice problems are something that I might put on the test, problems like those. So it's definitely worth looking at. So it's chapter 0. This problem, you've got two positive integers and an a. This notation here is standard notation for the natural numbers, which means the positive integers. Also sometimes written z plus, denoting all the counting numbers, sometimes called whole numbers as well. But n stands for natural number. We're assuming d is the GCD of a and n, and the goal is to show that ax mod n equals 1 has a solution. In other words, you can substitute something for x that makes that equation true if and only if d equals 1. And like I told you guys as you were working on it, the author doesn't state, but I think it's implicitly assuming n is bigger than 1 here. Because again, if you mod by 1, you always get a remainder of 0. This is really implicitly assuming without stating it. In other words, the author should have stated it, that n is bigger than 1, 2 or greater. It's an if and only if. IFF is shorthand for if and only if. Standard shorthand, you can always use that if you want. I've been encouraging you to think about scratch work and doing scratch work on scratch paper before you write things up nicely to turn in, because most people, including me, can't really do problems beautifully right from the start, most of the time. Though I'm going to try here because I did spend some time thinking about it as you were working on it. So I'm going to go ahead and write the proof, try to write the proof right away. As an if and only if, we need to do two directions, a left to right implication and a right to left. So if I do a rightward pointing arrow, that's a left to right implication. That means I need to prove that if this has a solution, then d is 1. The other direction, the right with a leftward pointing arrow, that would be a right to left implication. If d is 1, why does that have a solution? So suppose ax mod n equals 1 has a solution. You need to tease out what that means, first of all. This means there exists an x in Z such that, can you finish it for me? Well, maybe I should say there's another number as well. I'll suggestively call it Q. I should have put that all in one line. Can you finish that for me? Yeah, ax equals nq plus 1. If you didn't use the letter q, it's fine. If you used a different letter than x, actually, it's fine as well. I'm using a theorem there that's doesn't have a name with the word theorem in it. What theorem am I using? Division algorithm, yeah. Division algorithm is something we use so often. If you use it, you don't have to state it unless I explicitly say in a test question, make sure you name every single theorem that you use or something like that. I'll go ahead and just put it in parentheses here by the division algorithm. How do I use the GCD as a linear combination theorem? I suggested to use that. What's the key connection here? Or what's the key to connecting this equation to that theorem? and the fact of what we want to show D is 1. The theorem states for any non-zero integers a and b, there exist integers s and t so that the GCD of a and b is as plus bt. It's a linear combination of them. Moreover, it's the smallest positive integer of this form. And the corollaries follow so easily from theorems, they're essentially equivalent to the theorem. Or you can treat them as the theorem itself, essentially. An application of the theorem is a better way to say that. If a and b are relatively prime, then there exist integers s and t such that as plus bt equals 1. Actually, that's only stated as a one-way. If a and b are relatively prime, in other words, their GCD is 1, then that's true. But you really could say more, because the theorem has 2 sentences. The GCD is the smallest positive integer of this form. 1 is the smallest positive integer. So you could say more here. You could say, if there exists s and t so that this is true, then the GCD must be 1. Maybe that's the trickiest part, is realizing you could do that here. So what does that mean I should do with this equation? Want to say it, Macy?
Subtract NQ.
Yeah, subtract NQ from both sides. Therefore, AX plus, I'll write it as plus N times negative Q equals 1. Yeah, it's not, I guess, as the corollary stated here, it's not literally applying the corollary, it's applying the second sentence of the theorem. We have found a linear combination of a and n equaling 1. The second sentence in the theorem says the GCD is the smallest positive integer of this form. Therefore, since 1 is the smallest positive integer, the GCD's got to be 1. A and n have to be relatively prime. Does that make sense? I'll say it again here. I'll just say by the GCD is a linear combination theorem. It's really the second sentence of the theorem as stated. The second sentence says GCD of a and b is the smallest positive integer of the form as plus bt. In other words, a linear combination of a and b. We've got a linear combination of a and n equaling 1 here. 1 is the smallest positive integer that there is. And the GCD is the smallest positive integer you can make as a linear combination like this. Therefore, the GCD has to be 1. A and n have to be relatively prime. So they really could have improved the corollary. They could have made it an if and only if. All right, let's try the other direction. Suppose D, which is the GCD of a and n, equals 1. We need to show AX mod n equals 1 has a solution. Apply the GCD as a linear combination theorem right away. I'll just write it like this. GCD is a linear combination theorem. Implies there exists, I'll call them S and T like they do in the theorem, exist S and T in the integers such that AS plus NT equals 1. No Q's here anymore. But that's okay. I mean, the T is acting like the Q. And I'll just rearrange it the other way. AS equals n times negative t plus 1. And here's where it's good to also assume n is greater than 1. We now have as in the form of the division algorithm. It's like we're dividing by n times the quotient plus the remainder. But is that really the remainder? The remainder needs to be less than n, less than what we're dividing by. Yeah, here you do need to use the fact that n is bigger than 1. When you divide by 1, you always get a remainder of 0. But if n is bigger than 1, if it's 2 or greater, then definitely 1 is less than n. And it's definitely greater than or equal to 0. Therefore, by the division algorithm, 1 is the remainder that you get when you divide a times s by n. Therefore, as mod n equals 1. In other words, ax mod n equals 1 has a solution for x. It's the quantity s, the number s, whatever s happens to be. S is something specific here, depending on a and n. This is not the word as. I glanced at that and I'm like, is that the word as mod? No, it's as, a times s. By the division algorithm. That remainder is unique and it's greater than or equal to 0 and less than what you're dividing by. And yes, so n does need to be bigger than 1 here. Which I think in my answer key, I forgot to, I didn't notice that, I didn't think about it. So that was a flaw, not only in the book's description of the problem, but also in my answer key. But we're done. Praise the Lord. Okay. So if I put this on the test, it would be a pretty tricky one. I think it's definitely worth rethinking about. I'd probably give you the hint of using the GCD's linear combination theorem. It is, I have emphasized both here and in the lectures that that theorem is pretty important. So this is worth maybe practicing again in a week or two. See if you can reproduce that. It's a pretty important problem because it leads to an important fact in one of our main kinds of examples. The U examples, the U groups. Which ones have we considered so far? U8, U10, U12, something like that. Let's do another one. How about U14? Remember what these are. It's the group of units where the operation is multiplication mod whatever quantities in there, 14 in this case, as a set. It's the set of all positive integers less than 14 in this case that are relatively prime to 14. So anything that's not even and also not a multiple of 7 will be in this case. So 1, 3, 5, 9, skip over 7, 11, 13. That's a 6-element group. Again, the operation is multiplication mod 14. The 14 is like the n. And this problem that we just worked on is the theoretical justification for why all the other numbers are going to have multiplicative inverses. Because one is going to be the identity. The number 1 here in this group, because the operation is multiplication and not addition, is going to be the identity. 0 is the identity in Zn, because the operation is addition. 1 is the identity in this kind of group. And yeah, n here is 14. We're doing mod 14 arithmetic. So we've got a solution. A has an inverse x in un if and only if d is 1, the GCD of a and n is 1. So that's why I need to pick the positive numbers that are relatively prime to 14 to be the elements of U14. I pick something else like 10 or something, it's not going to have multiplicative inverse mod 14. There's nothing you can multiply 10 by to get a remainder of 1 when you divide by 14. There's also nothing you can get multiply 7 by to get a remainder of 1 when you divide by 14. I mean, 7, 14 is a multiple of 7, so that should make sense. All right, let's explore this group a little bit. It's got order what? What's the order of this group? 6, yep. I mentioned that, but notationally we can write this. Yeah, again, don't say absolute value, say order. Order of U14 is 6. The order of the identity element in any group is always 1. So there we write something that is true, even if that was an absolute value sign. But with the other ones, their order won't be equal to their value, probably. And the only one where it could possibly work is with 3, because we also learned on Wednesday what? That the order of an element or a subgroup, we saw, no, we didn't prove it, but we saw from examples, it has to divide what? It has to divide the order of the group. So yeah, 1 divides 6. For these other elements, whatever their orders are, they have to divide 6. So they can only be 2, 3, or 6 for their other orders. Can't have an order of 4 or 5 here. Let's see if we can figure out the order of 3. 3 squared is 9. And yeah, that would still be 9 even if we mod by 14. 3 cubed, well, of course, is 27. But mod by 14, I'll go ahead and be a bit sloppy here. I'll go ahead and write equals 13, mod 14. I mean, that's a little bit sloppy based on how we define the mod. It'd make more sense to say, to put the mod over there. 27 mod 14 is 13. If we're going to put the mod over there, it probably would be better to put 3 lines here and think of it as congruence mod 14. But the author is kind of sloppy here, and I'm fine if you're sloppy here. You can just write a regular equal sign. And yeah, go home and show your parents. See, mom and dad, 27 equals 13. We're not back to the identity there. The order of 3 can't be 2, it can't be 3. It has to be 6. Let's just keep going to confirm it. 3 to the 4th is, yeah, it's 81. But other tricks you can do, which are sometimes helpful, is you can use things you've already calculated, like 3 cubed is 13 mod 14. We can think of this as 13 times 3 mod 14 instead of 27 times 3. You're going to get the same answer in the end either way. 13 times 3 is 39. Mod 14 is 11. I mean, you can even be so sloppy as to not bother putting the mod 14 at the end of every line, at least. You should maybe remark at least one spot that you're modding by 14. And if we divided 81 by 14, let's see, 14, 28, 42, 56, 70. Yeah, 14 goes into 75 times, and the remainder would be 11 if you were dividing 81 by 14. There's only one element left. 3 to the 5th must be 5, because that's the only one left. We can think of it as 11 times 3. 33 mod 14 is going to have a remainder of 5. And 3 to the 6th better be back to 1. And that's the same as 5 times 3 or 15 or 1 mod 14. So yes, the order of 3 equals 6. In fact, because of that, we say that 3 generates the whole group. The elements of the group that you can get by forming powers of 3 include all the elements in the group. That's what it means to say it generates the group. So 3 generates this is official terminology, the group U14, i.e., another way to say this is that 3 is a generator. That's a more common way to say it, actually. Generator of U14. But you don't usually say generator, you usually say generator, right? Go faster. And we write a special kind of notation here. And we write U14 equals, here's what we do. We put pointy brackets around a 3 that look like a less than sign and a greater than sign, but they're not a less than sign and a greater than sign. In general, given a group G that's an abstract group, I'm not saying what group it is, and an element, call it little a in G, this symbol is called the subgroup of G generated by A. And it represents the set of all possible powers of A in the abstract. And in the abstract, the group operation is analogous to multiplication. If we were thinking about an additive group where the operation was addition, we wouldn't want to write powers. We'd want to write n times A, which means A added to itself n times, at least when n is positive. Here, actually, we do allow n to be 0 or negative. N is an element of Z. So we are talking about negative powers as well. A to the 0 power by definition is E, not the number E, but the identity of this abstract group. A inverse, of course, is the inverse of A. What's A to the negative 2 power defined to be? Well, you can define it in one of two ways. You can think of it as A inverse squared, or you can think of it as A squared inverse, and you have to show those are equal to each other. They are. To confirm that, you have to show the inverse of A squared is this. You'd have to multiply A squared times this and see that you get the identity. But what does A inverse squared mean? It means A inverse times A inverse Altogether, you got A times A inverse times A inverse. These two combine to give you an E. And then you get A times E times A inverse, which is A times A inverse, which is also E. So there's a little quick verification that these two things are equal. Plus the fact that inverses are unique. And A to the -3 power is defined to be either the inverse of A cubed or the inverse of A cubed. Those are the same words in the same order, weren't they? The inverse of A cubed, the inverse of A cubed. Depends where you put the emphasis. Yeah, then it's trickier when you have to write it out because you can't give it an emphasis. This is always a subgroup of G. I'm calling it a subgroup. Calling it a subgroup doesn't make it a subgroup. You have to prove that. I'm just realizing I forgot to plug my computer in. Just lowering the brightness. Did it lower it up there? Doesn't change the brightness there, does it? Okay, that's good. Calling it a subgroup doesn't guarantee it's a subgroup. That takes proof. We will prove it here still today. But it is a subgroup. It's certainly a subset of G. But is it a group under the same operations as in G? That's the question. And I claim it is. Is it an infinite set? Certainly looks like it's infinite, doesn't it? But hey, wait a minute. This example wasn't infinite. It would repeat. If we did 3 to the 7th power, that's the same as 3 times 1 is 3, mod 14. That's the same as 3 squared. Or excuse me, 3 to the 1st power. And 3 to the 8th would be the same as 3 squared. I mean, if you want to just extra confirmation, go ahead and compute 3 to the 8th as a big number. 3 to the 8th, 6,561. If I divide that by 14, I should get a remainder of 9, right? Because it's the same as 3 squared. Divided by 14, subtract 468, multiplied by 14, it should be 9. Yep. These group elements cycle as powers of 3, kind of like clock arithmetic, actually, right? It's like a mod 6 clock. But wait a minute, this is not Z6. Well, guess what? It's isomorphic to Z6. Even though the operation is multiplication here, and in Z6 it would be addition. Multiplication mod 14 here, in Z6 it would be addition mod 6. But they have the same structure. Their Cayley tables can be made to look the same with the same patterns to them. And therefore they're isomorphic. And they are both what we call cyclic groups. Cyclic groups is the main subject of chapter 4. Subgroups is the main subject of chapter 3. Cyclic groups is the main subject of chapter 4. Cyclic groups, not just examples, but in the abstract, with a bunch of theorems that are important. Is 3 the only generator of this group? U14. Do you have any intuition here? Is 3 the only thing you could use to get the elements by doing powers of 3? Any intuition? Good guesses? Do you feel like you're developing intuition? That's a guess, but an incorrect one. 9 squared is going to be the same as 3 to the 4th is going to be 11. 9 cubed is going to be the same as 3 to the 6th, which is back to 1. So 9 has order 3 in this group. The cyclic subgroup it generates consists of 1, 9, and 11. Right? Yeah. There is one more generator. It's 5. 5 is the other generator. And note that five, let's see. I'm pretty sure it's 5. Okay. Okay. And the reason I was realizing it's got to be 5 is because of the fact that it's 3 to the 5th. And 5 is relatively prime to 6. Is the intuition I had. That can be justified. But yeah, 5 squared is 25, mod 14 is 11. 5 cubed is 55, mod 14 is 13. 5 to the 4th is 5 times 13 is 65. Mod 14 goes into 56. This is 9. Yeah, it's got to have order 6 here. 5 to the 5th, 9 times 5 is 45. Mod 14 is 3. And 5 to the 6th is 5 times 3 is 15. Mod 14 is 1. 5 generates the whole group as well. "13 as 3 cubed and 3 divides 6 with the quotient of 2. It's got to have order 2. 13 squared has got to be the same as 3 to the 6th is 1. Yeah, 13 squared is 169. 169 divided by 14. 14 goes into 140. It goes into 154. It goes into 168. Yeah, 169 divided by 14 has got a remainder of 1. All right, let's end our class today by trying to verify that this is a subgroup of G. Not necessarily infinite, even though it looks infinite. Could be that these repeat. Certainly if G itself is finite, it's got to happen. These got to repeat if G itself is finite. If G is infinite, they may or may not repeat. Actually, if we think of what I mentioned on Wednesday, if G was, for example, C star, complex numbers take away 0 under multiplication, that's an infinite group. Infinitely many complex numbers, including if you just take away 0. But it's got finite subgroups, like 1i, -1, and -i is a subgroup of order 4, and the number I has order 4 under multiplication. The cyclic subgroup it generates has order 4. So how do you prove that this is a subgroup? Well, you got to know how to prove something is a subgroup. And again, the definition of a subgroup, I'm not going to bother writing it down, I'll just say it verbally here, is a subset of G that is a group itself under the same operation in G. There are three theorems in chapter 3 that qualify as what's called a subgroup test that you can use to prove something as a subgroup. First one's called the one-step subgroup test. Second one's called the two-step subgroup test, and actually maybe it's in the opposite order in the book. Okay, no, it's the same order. One-step subgroup test, two-step subgroup test, and one's called the finite subgroup test. At first, for most people, the two-step subgroup test is the one that's easiest to use. You might want to turn there, and I'll show it on the screen too. Page 63. Two-step subgroup test. I'm not going to prove these right now, and I mean, I think I proved one of them in the lecture, or maybe I don't, I'm not sure. Let's just see what they say and see how to use them. Let G be a group, let H be a non-empty subset of G. If A times B is in H whenever A and B are in H, in other words, H is closed under multiplication, the operation, and if A inverse is in H whenever A is in H, H is closed under taking inverses, then H is a subgroup of G. In other words, you don't have to verify associativity. That would follow from the fact that it's a subset. And do you need to verify E is in there? Well, not according to this theorem. E would be in there automatically, according to the theorem, is part of the gist of what the theorem is good for. Though, that said, even though this is called the two-step subgroup test, there are really three things you have to do. The first thing is so trivial that they don't even consider it a step. You want to show H is non-empty, which you can do many ways, but usually the easiest way is to show that E is in the set. Okay, so let's do this. Let's prove. Okay, so let G be a group. And let A be an element of G. Prove that the thing we're calling the cyclic subgroup generated by A, the set of all powers of A, is a subgroup of G. Special notation here I want to mention as well. Notationally, we write the cyclic subgroup generated by A is, this looks like a less than or equal to. It's not. This is our special notation for is a subgroup of. Lots of confusing notation here. Is a subgroup of. You have to tell from the context. These are not numbers. These are sets and evidently groups. Use that notation when it's a subgroup. Contrasted with subset notation, which you can always use whenever you've got a subset. Only use this notation when you got a subgroup. It's not just a subset. All right, again, I don't recommend doing proofs without doing some scratch work, but for the sake of time, let's do it here. So I'm going to use the two-step subgroup test, but the first thing I have to do is the 0th step is verify that H is non-empty. I guess I didn't have to call it H. Since, well, it's obviously non-empty. Right? It's elements of this form where A is a specific element. It's obvious. Okay, let's be a little overbearing here. Since A to 0 is E, E is in the cyclic subgroup generated by A, so it's non-empty. Oh boy, that's kind of crazy that I even bothered writing that. I mean, I could also say also, this is not empty since A is in it, or since A squared is in it, etc. This one's so trivial that it almost feels crazy just even writing it down, but do humor me and write it down anyway, something like that. Verify when you use this two-step subgroup test, or the one-step subgroup test for that matter, that the set is not empty. I mean, it's so obvious here, you could get away with saying obviously or clearly the set is not empty. Sometimes it's not always so clear. Okay, there are situations where it's less clear. Now assume, I'm going to not use A and B here because I've already had a use for A. Let's say X and Y. X and Y are in here. We must show two things. These are the two steps of the two-step subgroup test. One, X times Y is in here. And two, X inverse is in there. Or Y inverse is in there. It doesn't matter since those are arbitrary symbols. Got an idea what to do here? I mean, you got to use what this thing means, this symbol means here. You got to use that. That's relevant. Since X and Y are in that set, there exist integers, call them M and N. Such that what? Because that's what it means to be in that set. Therefore, X times Y is A to the M times A to the N. The question is this product in this set? The answer is yes, but what should I use to verify that? Can I just write that and say I'm done? No. What should I do? Do what you would do even if you knew nothing about groups here. If you just thought these were numbers, add the exponents. But wait a minute, is that allowed? Yeah, if you look back in chapter 2, you'll see it's allowed. Chapter 2 in the reading. They mentioned this is true, and this is true even if G is not commuted, even if the group is not commuted, not abelian. What's not true when the group is non-abelian is if you got two distinct elements, you multiply them and raise that to the n. This is not true if G is non-abelian. This only works when G is abelian. But this kind of exponent rule works no matter what, which should make sense. I mean, if you pretend M and N are positive, this means A multiplied by itself M times. This means A multiplied by itself N times. And altogether, you'd have M plus N A's if M and N are positive. Now, M and N could be negative here. It still works. That would take proof. but you can use it. So this is in here. Also, x inverse is a to the m inverse. Another property of exponents that you may use is that you can swap these around. This is the same as a inverse. Well, a to the negative m power. Multiply those exponents. And that is a power of a, so it is in here. Therefore, by the two-step subgroup test, this set is a subgroup of G, which you can write like this. Raise the look. Okay. We're starting to get now, as we get into chapters 3 and 4, into the meat of the course. Examples are still really important, but so is the theory. Take the theory seriously. Make sure you understand these definitions and theorems. Make sure you understand the proofs too. Even if it's confusing at first, you have the capability of understanding it given enough time. Okay, so make sure you make the time as well. Okay, have a good weekend.